Welcome back. Today we want to talk about chemical bonding. Now previously we've talked about elements, mixtures, compounds, and molecules. And all of those molecules become molecules because of chemical bonding. So we want you to understand the differences and how that actually occurs. Now, with that in mind, our learning targets for today are for you to understand what chemical bonds are and what subatomic particle is responsible for that bonding. We also want you to recognize that there are different types of bonds and understand that valence electrons and identify those valence electrons in different elements. So chemical bonding, just taking a step back, is really the force of attraction that holds two atoms together. And that is basically a result of the rearrangement of the electrons between them. So in order to have a bond, we really need to have an attraction between atoms. Now, we have two different types. The first one is covalent bonds. So if you think about the word covalent, co means to share, and valent is basically something you're going to learn a little bit later. But basically, if you think about it, it's sharing electrons. So if you had a co-worker or just somebody who is a co in something, a co-teacher, those people or those situations, we have things that are shared, responsibilities that are shared, etc. So we're looking at shared electrons. And so the same thing is true in bonding. We have a situation where electrons are shared between two atoms. So we've got two atoms coming together here. These are the electrons that are in the outer shell and in the outer shell of this one, and they're sharing these last two electrons, which is making their outer shell complete, which we've talked about before. The reason that atoms tend to bond is because they want to be stable. They want those outer shells to be complete. Now the other type of bonding is ionic bonding, and that's when we have atoms that transfer electrons from atom to atom. And so as you can see, electrons are really the particle of the atom that are responsible for bonding. So an ionic bond is where we're going to have a transfer. So if we have, our example here is sodium, which is Na, and fluorine, which is F. Now we're showing the electrons in the shells and the diagrams that you're used to. Na has 11, so there's 2 in the first shell, and you can see there are 8 in the second shell, and we're not really seeing the shells here, but this is how it looks. And then we have 1 in the outer shell. Fluorine has 9, so there's 2 in the first shell, and then we have 7 in the second shell. Now in an ionic bond, one atom is going to give up electrons to the other one. Now because Na only has 1 in their outer shell, it really wants to have a stable or a complete outer shell. So it's easier for this one to give up this electron and have this electron move to this atom, leaving this as a full outer shell. So if that happens, this one is actually going to join fluorine, creating 8 in its outer shell, leaving it more complete and more stable. We're going to talk more about ionic and covalent bonding as we go, but we want to kind of give you an idea of how it happens. Now, it occurs with those electrons that are found in those outer shells in the electron shell. The electrons are called valence electrons, and basically they are the highest energy level, and they're held most loosely by the atom. So those valence electrons can be found in your periodic table of elements. We're going to show you how to find those as we move on today. Now again, this is a kind of a small version of your periodic table of elements, but just having an awareness of where these things are on the periodic table will help you be able to identify the valence electrons and how atoms are going to bond. Now the valence electrons of an element, those are the electrons that can participate in the formation of a chemical bond. So it's the number of electrons we have available for bonding. It also determines the properties of that element and whether or not it can bond with another element. Now our main group of elements, the ones that you're going to see there, are going to be the ones that we see in the outer shell. And here we go again. We love this when this does this to us, don't we? Well, we're just going to go a quick little review, aren't we? The main group of elements are really groups 1 and 2, as well as these groups here, which are 13, 14, 15, 16, 17, and 18. The transition metals do bond, but they can be in an inner shell, so we're not going to really touch the bonding with transition metals today, or actually in this unit in general. We are going to work mostly with the main groups of elements because those rules that they have for bonding are pretty consistent, so it's easier for us to understand. Now, some examples of valence electrons, you'll see, if I have Si, I've got the Bohr diagram here, and so you have 2 in the first shell. Si is number 14, so it should have 14 electrons. You'll see 2 in the first shell, we see 8 in the second shell, and the last shell has 4. So, basically, if we remember that the first shell holds up to 2, the second shell holds up to 8, and that third shell holds up to 8 as well, that brings us to our electron dot configurations, which helps us understand how these elements or these atoms will bond. You'll see that we've got our periodic table here kind of in condensed form. You have hydrogen on the left, which is number 1. You've got helium over here on the right, that's number 2. And then it follows with lithium, which is number 3. Now notice that lithium only has 1 dot here. That's because with the electron dot configurations, we only show the outer shell. So lithium has 2 in the first shell because it's number 3, and it has 1 in the second shell. Likewise, beryllium, which is number 4, has 4 electrons, so there's 2 in the first shell, 2 in the second shell. Boron is number 5, so it's got 2 in the first shell, and we're showing the 3 in the outer shell here, and so on. So you're going to see that as we move all the way across. Now, this is what's following the octet rule. So the octet rule really is that all of the atoms want to have at least 8 in the outer shell, unless of course it's one of the smaller ones and they only want to have 2 in the outer shell. And that would complete that outer shell for them. But otherwise we're looking to have a full octet, or a full 8 in the outer shell. Now, those electron dot diagrams follow specific rules. Each element has a specific number of valence electrons ranging from 1 to 8. So it gets trickier with the bigger numbers, but I'm going to show you a little trick as we go. So for example, if I have atomic number 10, that has 10 protons. That's how come it's atomic number 10, or the reason why. And it also will have 10 electrons if it's neutral. So the figure below depicts the way that you would show the valence electrons in that element. Now that happens to be neon, and so each dot stands for one of the valence electrons. So neon has 2 in the first shell, and then we're showing the 8 in the second shell, and that is how you would draw the dot diagram for this particular atom or element. Now, and as we go through it again one more time, we'll see that we have some other depictions for you. We have hydrogen, which has 1. We have carbon, which has 4 in the outer shell, and we have oxygen that has 6 in the outer shell. So, if we look a little bit further and we see our box for hydrogen, hydrogen's number 1, okay? So it has 1 electron, only 1 in that shell. Carbon is number 6, so it has 6 in the outer, 6 electrons, 2 in the first shell and 4 in the second shell, and that's shown here in a dot diagram. And the same thing then would be true for your oxygen. Oxygen is number 8 on the periodic table, so it has 8 electrons. And in the first shell it would have 2, the second shell it would have 6, and it would have 2 open spaces for electrons to actually be transferred to it. But this is what it would look like in its dot diagram, showing us that we are too short of having a full octet. Now, I want you to take a minute and pause and draw the electron dot diagram for calcium. Now, calcium is number 20 on the periodic table, so that would mean that calcium has 20 protons as well as 20 electrons in an atom that does not have any kind of ionic charge. So, if we look at calcium and the depiction of it, we've got 2 in the first shell, 8 in the second shell, 8 in the third shell, and we have 2 in the last shell. So that should mean that calcium should be shown as having 2 dots in the configuration for the dot configurations for us. Actually, we call them the Lewis dots. And you'll understand that a little bit more as we go as well. Now, here we go again. It just keeps doing it over and over again. Isn't that great? Now, one of the ways to kind of make this easier for you, one of the tricks that I have for you, is that if you look at the periodic table, and if we really don't pay any attention to these transition metals, because again, those rules don't always apply, if you number your periodic table on the top, and you can kind of see that yours is actually numbered with Roman numerals, and for the most part that's going to follow the same pattern. So you'll see that this one is Roman numeral 1A on yours, and then 2A, and so forth. But if we have number 1 over here, number 2, and then we go all the way across to boron, which is number 3, you'll see that this is Roman numeral 3A, 4A, and so on. And so basically, if this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8, that will help basically all the way down the row. That's how many electron dots you're going to have in the configuration in the outer shell. This is how many electrons can actually be used for bonding. So for carbon, it would be 4 electrons could be used for bonding, up to 4. Nitrogen and all of the ones in the nitrogen family have 5 in the outer shell that can be used for bonding. And so when we do the dot diagrams, we would basically draw 5 dots there. So those are the basics, and we are going to work on different types of practice that you can do, and also a little bit more on ionic bonds as well as covalent bonds in our next lesson. We'll see you again soon.